Hello everyone. Today we're going to be learning about resampling in machine learning and deep learning. Firstly, we're going to talk about what is resampling. Then we're going to see some examples of the resampling methods. Then we're going to prove some formulas and see some interesting applications of resampling. So why do we need resampling? Firstly, when we have an imbalanced data set, let's say we have only 5% case of positive kidney disease cases and others are negative. So in order to avoid overfitting the data and in order to not neglect the cases, we must use resampling to get some better computation and to also test out our model's performances. Why though? Because new data is not always available to test the model. So our goal is to use the data that we already have as much as possible and as optimal as possible. So what could we do here is firstly, let's say we want to check if a quadratic line fits the model performs better or if the cubic model performs better. So in order to check that, we firstly could divide the data set by 50-50 to train and test set. So as we see here, we divide the red one is the test one and the black one is the train one. So how much spent on video games depends on age, let's say, and we firstly perform training on the black dots. Let's say it looks like this on the cubic, uh, then it looks like on the second part we do the same, but we choose randomly another set of 50-50 division. Then it looks like this, and then we perform the mid. We perform the mean squared error, but we do it several times, and then we compare the mean squared error of each and every of these data sets. So we see here that the variety is very huge. So let's say this one uh, and this one are located here. So we see that they're very different from each other, even though the shape is the same. This is all because dividing the dataset by 50-50 is actually quite a lot. That means that we omit half of the data for training. We might miss out some features. We might miss out on many important data points. So we get this high variety of the performances. This is not good. So in order to fix that, we may use leave one out cross validation. So we see here that we only use one data point as our testing set, and others are just training sets. So how do we do so? We as the previous example, we do it several times. In this case, we do it n times, approximately n times. We compute the value of this curve, then we test it on this test. We compute the value of this curve, then test it on this test. Then we compute the mean squared error and average them all based on how many times we tested it. But it's quite cost expensive because n times computing the model is quite a lot. To fix that, um, we can use the leverage. So what is leverage? Leverage is how much the point affects the curve. Let's say this point has low leverage because when we remove it, right? When we remove it, the line doesn't change. The line almost doesn't change. But if a point was here and then it was removed, the line would actually change drastically. So higher the leverage, higher the importance of the data point. So we can actually calculate the leverage of each and every point. And when we actually compute the cross validation, we can just apply this formula to punish the MSE by how important that data point is. So if a data point is important, we punish it more because 1 minus big number is actually small number. So that drastically will levitate the value of the mean squared error. So this might actually help us to calculate the MSE of each and every point without actually running the tests like n times. But still, this model suffers from uh, overfitting because, yeah, well that's because we only use one test and like the other data points are quite the same. So every time we will see the same, almost the same graph, almost the same line that are tested on different test data points. And next, to combat this, we actually can use k-fold cross-validation. But as we see here, leave one out cross-validation is just a special case of k-fold cross-validation. Because in k-fold cross-validation, we choose a certain k, let's say 5. Then we divide the data set by 5 folds. So we divide it by 5 folds, and then we choose one as test, as we see here. So these ones are testing sets, and the rest is training. So we train the data on the black dots, and then we test them on red. We do the same several times, uh, and we then compute the MSE and then average them. And when we compare them both, we actually see that uh, mean squared error of tenfold CV that is run 9 times, uh, we see the variance, the variety is very low. Like they're almost the same to each other compared to uh, compared to 50-50 validation. It's all because, well, there's a lot more training set. Training set is we do not omit the half of the training set. Then we run it multiple times and then test it multiple times. We actually see that it performs quite well. So we can actually see which degree of polynomial is the best fitting to something. Uh, and then we see the LOOCV, which is like, as we see, as I told before, which doesn't drastically change from case to case. So after we compute the MSE and then average it, well, it's pretty constant over sets. So we actually might compare it to real data, real mean squared error. Usually we cannot compute the mean squared error because we don't know it in real life. But if we simulate data, we can find it. And we can see here that the shape, almost all the time, the shape is almost the same. Except we tend to underestimate the data, but it's not important because what we actually care about is finding the level of flexibility that we need, which is not that different from the true value, as we can deduce from these graphs. Especially the rightmost graph, we see that it's almost the same. Even though they underestimate the error, we don't actually care about the true error. We care about which flexibility gives us the least error. So moving forward with resampling methods, we need to learn about Bootstrap method. But before that, let's just consider some simple example. We have two sensors X and Y, which calculate the room's temperature. I drew this chart, and we want to estimate the real temperature in the room. So how can we actually estimate the real temperature based on these two sensors? So we should find some alpha that is a combined estimate of how much we trust both of them, right? So let's say alpha is how much we trust the X sensor, and 1 minus alpha is how much we trust the Y sensor. So we cannot trust both of them by 100%, right? We either trust them 50-50 or 70-30. But how do we find the alpha? Well, we can find it out by some simple calculus and mathematics. So the temperature is this equation. Then, well, we know that variance of t is actually variance of this whole expression. So how do we actually expand these brackets, well, we have this formula from statistics, and we can actually expand it. And after we expand it, we can find some like values, some like expressions. After we combine these like variables, we can see that it reminds us of a quadratic equation, right? Over form x squared c1 x c2 plus c3. So we see that the x here is alpha, so alpha is our variable. And then we can see that quadratic function, uh, that we can see here that the slope of the graph, where the slope is 0, is actually the minimal point. So we can use the first derivative to on this equation. We find out that this derivative looks like this. Then we find the alpha when this whole expression is 0, because the slope is basically 0. So by swift calculations, we find out that the alpha is actually this value. Hence, we can find the alpha if we can find the variance. Well, we see here that the statistical values are this. Then we can find alpha. So we see here that the trust tensor x 4 times higher than the trust tensor y, but it's only in this case, in this chart. So to be more accurate, we will use several charts, let's say on different days or something, just new data of the same sensors. So we, after running it several times, we get the same approximate of 0.7, let's say, and we also can find the variance of the alpha, of how does the alpha change when we change the data set. But new data is not always possible. So how do we find the variance of alpha when new data is not possible? That's where the bootstrap kicks in. So how does the bootstrap method work? Um, so we have, let's say, 3 observations, only 3, and we cannot have new observations. So in order to find alpha, um, we sample them randomly. Let's say we choose one of the 3 observations. They have a same probability of being chosen, and then we put them in a box of the same size. So on average, 2/3 of the data is chosen. So as we see here, 3, 3, 1 is 2/3 of the original data. But we use it to find the alpha here. We use this data set, the new sampled data set, to run the finding of alpha function. And then we do that several times. We do that many times. We find alpha, and then we find the average of alpha, which is the alpha itself. And then we can find the variance of alpha. So this is how the bootstrap works. And let's actually see if the bootstrap method actually performs well. And it does, as we see here. Let's say our alpha on true values is 0.6. The bootstrap method performs almost the same. It has the same alpha almost. And then we see that the shape of the curve is almost the same. And we mathematically see when we actually run these 2 simulations, we see that the variance of alpha is always, let's say this alpha star, is almost the same, almost the same. And we see here the performance is almost the same as when we have new data. And let's see some interesting applications of the bootstrap method. So bootstrap method, uh, in a recent research paper, it was used for cross-validation estimate. That's actually pretty funny because cross-validation and bootstrapping are both uh, resampling, but we use bootstrapping to see how much our cross-validation is certain, how much we are confident that the performance is such and such. So we see here that this is the plot. This is the plot of our uh, Bootstrap cross-validation estimate. Um, how does it work? So we know that cross-validation is dividing the data to chunks, k-folds. Let's say we have k equals 3 here, um, and we see it right here. The observations are false. So we see the 3 faults here, and then among them we choose 3 of them randomly with the same probability. And as we know, only 66% of the data is always included. So there will be some data that is repeated, as we see here, 3 and 3. And if we use these two as training set and then use this one as testing set, we see that we already used this data set in the training set. So the estimate of our error will be very low. So we cannot use bootstrapping naively. So in order to fight this, what the paper came out with briefly is we actually control the size of our sample. Let's say this box. Uh, so we delete the 33% of our data that is in this sample. We do not use it and only use um, this as training and then use this as test. Actually, it will look a lot better because we will have a lot more chunks and we will remove 33% and then use this. But here we have only 3 for simplicity. So we do that several times. We do that many times. We compute the alpha. And then this alpha is the error of our cross-validation. And we find it here. And then we see that we can actually calculate the variance. We can actually see the confidence interval. We can compute the confidence interval here, let's say the bottom 5. So we can actually say how certain we are that in the how certain we are that the true value of error lies between something. So let's say we are 90% certain that the value of alpha is here. So this is one very interesting uh, usage because using cross-validation only once and then saying that, oh, that this is our model's performance is actually not so rigorous. We cannot actually assess the assessment of our model because it all depends on the training set, right? So this is actually a very interesting application. Um, so thank you very much for your attention. I hope it was interesting and entertaining a little bit. We learned resampling methods, variance, we saw a simple example of trusting sensors. So thank you so much. Hope it was useful.